Greetings 347 fans, and welcome to our video part 1 of an examination of first order differential equations which are classified as autonomous. In this video part 1 we'll see a motivating problem for what we'll later call qualitative analysis, and we'll also see an analytic criterion that will sort of supplement that qualitative analysis. Keep in mind in this video, one of the things we're going to be doing is actually trying to determine as much as we can about a solution of a differential equation without actually solving that differential equation. So a little bit of motivation. Many problems lead to models that have no explicit dependence on the independent variable, which again is usually time. So such problems or such differential equations are called autonomous. Now, an autonomous differential equation is necessarily separable. However, separating variables and finding an explicit solution by integrating is not always that easy of a task. So for the first time here, we're going to be, again, having a look at differential equations and trying to glean as much information about the solution of the differential equation by just looking at the differential equation itself, not by finding an explicit formula for the solution. Okay, and again, that's going to be called qualitative analysis. So as a motivating problem, we're going to go ahead and have a look at the logistic growth equation. So the logistic growth equation is an equation that models population growth, and it can be derived by making two assumptions about the relative rate of change of a population. So the first is that the relative rate of change is equal to the difference between birth and death rates. And then the assumption about the birth and death rates are that the birth rate is a linear decreasing function of population and that the death rate is constant. Now there's some key words here we've seen before. So rate of change, of course, means derivative. We've seen relative before too. Relative indicates that you're dividing out the population size. So here, relative rate of change means x prime over x. A linear decreasing function of the population might be something like beta naught minus beta 1x, and a constant death rate here, delta naught. So you can think of maybe an increasing population have a crowding effect and causes a decrease in a base birth rate, and maybe populations die at the same relative rate independent of population size. So putting those together, x prime over x is equal to beta naught minus beta 1x minus delta naught is relative rate of change is equal to the difference between birth and death rates. So we can take this this differential equation for x and rearrange it. It turns out to be convenient first to group the beta naught and delta naughts together, factor those out of the equation, and then rename constants. So here I'm going to go ahead and call beta naught minus delta naught r, the relative growth rate, and I'm going to call the constant in front of x actually 1 over that constant. The reciprocal of that constant is k. If you have a look at units, it turns out that beta naught and delta naught both have units per time, whereas the constant k has units of population. Again, r is the relative growth rate for x small, and k is called the carrying capacity. We'll see why it's called that in a minute. Okay, so here is our logistic equation, just moving the x in the denominator on the left-hand side to the right-hand side. We have x prime equals rx times the quantity 1 minus x over x over k. Again, this is an autonomous equation. It's of the form x prime equals f of x, where f of x in this case is just a quadratic in x. Okay, so we've seen autonomous equations a little bit before. One thing we can do with autonomous equations is have a look at equilibrium solutions. I'll remind you that equilibrium solutions are values of the unknown function x that make the right-hand side 0. Any constant value that makes the right-hand side 0 is necessarily a solution of an autonomous differential equation. And here in the factored form, we can see quickly what those solutions are. X of t equals 0 and x of t equals k are equilibrium solutions. Okay, a second thing we can do is have a look at a graph of x prime versus x. So of course, x prime is equal to f of x, and f of x is just a quadratic in x. Here we're thinking again about x as the horizontal axis, as almost an independent variable in this part of our argument. So a quadratic in x with a negative coefficient on the x squared term opens down, and here we see our quadratic opening down, intersecting the x-axis at those equilibrium solutions at x equals 0 and x equals k. Now, one thing we can do is think more carefully about the information that x prime gives us. Remember, x prime is the slope of the unknown function. It's the slope of x. And of course, if x prime is positive, that means x is increasing, and if x prime is negative, that means x is decreasing. So when x is greater than k, the quadratic is negative, and we can see that x ought to be decreasing in that area. Similarly, when x is between 0 and k, the quadratic is positive, so x ought to be increasing there. And we could talk about x less than 0 too, but we won't in this case because we're looking at a population model, and we don't really find it necessary to think about negative values of the population, but you could, and in this case, the solution would be decreasing over there too. So I'll go ahead and add some arrows along the x-axis to indicate whether x is increasing or decreasing in the particular region. And it looks like as long as you start with a positive value of x, that either you increase or you decrease and move toward k. So it appears that as t goes to infinity, x of t approaches k for most initial values. One initial value for which that doesn't happen is when x is equal to 0, and the interpretation here for that critical point or that equilibrium solution is that if you start with a 0 population size, you should stay at a 0 population size. However, if something happens and you get bumped off that 0 population size, it appears that you approach the population size of k. And indeed, if you start on the population size k and get bumped off of k, you come back to k. Okay, so now we see why k is called the carrying capacity. It looks like that's the preferred population for this particular model. As time goes to infinity, it appears that x approaches k for most values of x naught, for most initial values, for most places you start. Accordingly, we say that x of t is unstable. When you get bumped off, you don't come back. And we say that x of t equals k is stable. And you can classify stability as answering the question, if you get bumped off the equilibrium solution, do you always come back? And we'll see more of that in just a minute. Okay, the last thing we can do is transfer this information in the x prime plane to the tx plane. So all we have to do is identify first equilibrium solutions. So here are those equilibrium solutions at k and 0. And then, of course, our solution, our unknown function x, is increasing between 0 and k, decreasing when x is greater than k. And we can see those arrows now on the vertical axis, the vertical axis now being the x-axis, and plotting those solutions as a function of time. So again, we can see why k is called the carrying capacity, and we can see why 0 is an unstable equilibrium solution while k is stable. So just to summarize here, what we've done is called qualitative analysis. So qualitative analysis on the logistic equation, we identified zeros of the right-hand side. We constructed the phase diagram or plotted x prime versus x. And then we were able to classify stability of our equilibrium solutions and transfer that information about the phase diagram and stability to curves in the tx plane. So here x is a function of t. And again, here's a whole lot of qualitative features of the differential equation, or really the solution of the differential equation, without finding an explicit formula for that solution. Okay, so in general, that's what qualitative analysis means. Qualitative analysis includes finding zeros of the right-hand side. Zeros of f are called equilibrium solutions of the system. So solving f of x equals 0 is a job we can do. And again, this solution helps us identify what's going on in the phase diagram. So plotting x prime versus x is called the phase diagram. This is a graph where x takes on a role as an independent variable, and we plot the right-hand side x prime or f to tell us the sign of f. Again, gives us whether x is an increasing or decreasing function. Behavior of solutions near equilibria classifies stability. The technical definition, I've been saying stable, but the technical definition is actually asymptotically stable. For the purpose of this class, we're not going to discuss the difference between asymptotically stable and stable. We'll just call our equilibrium stable if any solution that starts close to an equilibrium solution approaches that equilibrium solution as time gets large. Okay, and finally we say that an equilibrium solution is unstable if it's not stable. And we can use all that information from equilibrium solutions, phase diagram, and stability to transfer and sketch solutions in the TX plane. And again, the first job here is to sketch the equilibrium solutions and then identify where the slope is positive and negative here, so where x is increasing or decreasing, and then just connecting up the slopes. And again, the key to this is that the sign of f gives us the slope of the desired solution x of t. Okay, so an example that's not a population model, here's the autonomous differential equation x prime equals negative x to the fourth plus x squared. So here we'll go ahead and do qualitative analysis, which again consists of identifying equilibrium solutions, drawing a phase line diagram, classifying stability of those solutions, and then sketching solution curves in the TX plane. Okay, so the first job is identifying equilibria. I'll remind you that equilibria are values of x where the right-hand side of the differential equation is 0. So in this particular case, it helps to factor the quartic. We factor the quartic and see that the remaining quadratic factors like a difference of squares makes it easy to identify equilibrium solutions. Those equilibrium solutions are 1, 0, and minus 1. From that, we can construct a phase diagram. So again, the phase diagram is just a plot of the right-hand side. We've been calling that little f of x as a function of x, thinking of x as an independent variable here. So in this particular case, x is a quartic that opens down, and we know where its zeros are at minus 1, 1, and 0. And we can add to that phase diagram arrows that indicate the sign of f, or whether x is increasing or decreasing. Wherever f is negative, x is decreasing. So for x less than minus 1 and for x greater than 1, the quartic is negative, so x is decreasing. And between minus 1 and 1, of course not including 0, one of the equilibrium solutions, we see that the quartic is positive, so x is increasing there. So again, to address the question of stability, imagine that you are standing on an equilibrium solution and that you get bumped off. Ask yourself the following question: do I always return to the same equilibrium solution? If the answer is yes, the equilibrium solution is stable, asymptotically stable really, but we'll call it stable. And if the answer is no, then the equilibrium solution is unstable. So I think it's quick to see that minus 1 is unstable, right? If you're standing on 1 and you get bumped off of it, you either move toward 0 or you move toward negative infinity. Similarly, the equilibrium solution at 1, the blue one, is stable. If you get bumped off of 1, you come right back. And finally, the equilibrium solution at 0 turns out to be unstable. Some textbooks might classify this as semi-stable or half-stable. We won't do that. We'll just call it unstable because it's not stable. If you get bumped off to the left of 0, you do move back to 0. But if you get bumped off to the right, you move toward 1. So we can see that you don't always move back, which is the definition of unstable. So x equals 1 is stable, x equals minus 1 and 0 is unstable, and we can transfer that information to curves in the TX plane by first plotting those equilibrium solutions, identifying where slopes are positive or negative with some arrows on the x-axis. Again, x-axis here is the vertical axis, so I'm just transforming those arrows on the x horizontal axis in the phase diagram to the x vertical axis in the solution curves, and then playing connect the dots with increasing or decreasing. So we can see here that stable behavior at 1. If you get bumped off of the solution at 1, you don't come back. And we can see again the unstable behavior at 0 and minus 1. If you get bumped off minus 1, you don't come back at all. And if you get bumped off 0, you might come back, but you might not. Okay, So that's it for a motivating problem, as well as sort of a summary of qualitative analysis and an example illustrating qualitative analysis. Part 2 of this video will have a look at the analytic criterion for stability and bifurcations. So long for now, and we'll see you again soon.